Alright, so let's start by understanding this problem. So over here we are given a binary search tree and two nodes P and Q, right? And our task is to find their lowest common ancestor, or LCA for short. And by definition, the LCA of two nodes P and Q in a binary tree is the lowest node that has both P and Q as descendants, including the possibility that a node can also be a descendant of itself, right? So let's actually visualize it with an example BST over here. So in this given binary tree, for instance, if P is equal to 2 and Q is equal to 8, then the LCA will be 6, right? And why 6? Because that's where the path of 2 and 8 diverge, right? On one side of 6, there will be 2, and on the other side, there will be 8, right? So this is actually the split point, and that's why 6 is the LCA over here. Now let's consider another example. Let's say P is equal to 2 and Q is equal to 4, right? Then the LCA will be 2, because node 2, if you see, is actually the ancestor of node 4, and by definition a node can also be a descendant of itself, right? So 2 over here is actually the LCA in this example, right? So that's the entire problem statement. Given a binary tree and two nodes P and Q, we need to find the LCA of those two nodes in the given binary tree, right? So now maybe you can just pause this video and try to think of a solution, and once you're done, you can just come back and check the solution. Okay, so let's now break down the intuition behind solving this efficiently. Now the beauty of this problem lies in the properties of a binary search tree, right? That is, all the values of the left subtree of a node are smaller than the node, and all the values in the right subtree are larger than the current node, right? And using this, we can actually navigate the tree with a simple rule-based approach. So first of all, we will start from the root node, right? And if both P and Q are actually greater than the current node, we go to the right. Else, if both P and Q are smaller than the current node, we go to the left, right? Otherwise, if one is on the left and the other is on the right, or if one of them matches the current node, then in that case, the current node itself is the LCA, and we return that as the final output. So that's the intuition that we are going to follow, right? Now maybe let's simulate this logic step by step with concrete values, right? So over here, if you see, first let's suppose P is equal to 2 and Q is equal to 8, right? So we start at root node 6, and since 2 is lesser than 6 and 8 is greater than 6, the current node itself is actually the split point, because P will fall on the left of it and Q will fall on the right of it, and hence the LCA over here is 6, right? Now let's try with P equal to 2 and Q equal to 4, right? So we start again at 6. This time both P and Q are less than 6. So we move to the left child, which is node 2. Now at node 2, one of the node matches 2, and the other node, which is node 4, actually lies in the right subtree. Hence 2 is the lowest node that connects both P and Q, and so the LCA over here will be 2. So as you can see, each decision is being made on pure comparisons in this algo, and there is no stack or recursion needed over here, right? So that's the entire algo. Now let's walk through the actual Python implementation of this, right? So we begin with the definition of a tree node class. Each node stores a value well and has pointers to its left and the right children, right? Now inside the solution class, we define a function called lowest common ancestor that takes in the root of the BST and two nodes P and Q. Now we initialize a variable current node and set it to the root. And this will help us traverse the tree iteratively, right? Now we start a while loop over here that continues as long as the current node is not null, and this loop will help us walk down the tree. Now inside the loop, we first check if both P and Q are greater than the current node value. If so, the LCA must be in the right subtree, so we move to the right. Else, if both P and Q are smaller, it means the LCA lies in the left subtree, so we move to the left. And finally, if neither of the above conditions hold, it means P and Q are on the opposite sides, or one of them matches the current node. And so this will be the split point, and we will return the current node as the LCA, right? Now this logic, if you see, is not only concise and readable, but also highly efficient, leveraging the BST's ordering rules to avoid unnecessary exploration, right? Now finally, let's look at the performance. So talking about the time complexity over here will be order of h, where h is the height of the tree, and in a balanced binary search tree, this is going to be order of log n, right? But in the worst case, it can degrade to order of n if the tree is skewed on one side. That is, all the nodes are present in a sorted order from top to the bottom. In that case, the height will be equal to the number of nodes in the tree, and so the time complexity will also become order of n in that case, right? But in a balanced binary search tree, it will be order of log n, right? Now talking about the space complexity, it will be order of 1. It will be constant since we are not using recursion or additional data structures over here, right? So that's the entire solution of this very important interview problem. I hope you understood it well, and now I will see you in the next one. Happy coding.